Hey everyone, great to not see you, but great to be on a Brainfood Talk again. It's been a while. I'm happy to share some thoughts which I had over the last couple of months or even years today here in this format. I'm really happy to be there, to have the opportunity. I know that we at Square have a lot of people who do these Brainfood Talks from time to time. So it's actually not that easy to get a slot anymore. So I'm very humble to have the possibility to present here a topic, which lives quite close to my heart, I would say. And this topic is about architecting for scale. And if you follow I would say my social media, my Twitter, my LinkedIn for a while, you probably know that I, talk about these things, think about these things quite a lot, because I often have the feeling that we are as an industry in a phase where we obviously need to scale our engineering, right? Software eats the world. Each company is a software company. All these phrases which basically tell us that we are building more software than ever before, and that's what I find quite interesting, because we work a lot, on optimizing flow when it comes to software delivery. We work a lot on, improving things that we, as organizations, can better deliver software. But the interesting part about, software delivery is that it's such a strongly, I would say, social technical aspect or thing where we usually need to understand the organization, where we usually need to understand the product, right? But where we also usually need to understand the technical means. And in this talk, I would like to dive a little bit deeper in what basically makes us scale as organizations and how can we architect for this scale. So what is basically the technical foundation to do so? So I would say let's jump directly into the slides to not um, lose any further time to discuss about this. So the art of architecting for scale. So for those who do not know me, so who am I? Why should you, or why should you listen to me, or why can you maybe listen to me? I'm David Leitner. I'm a principal engineer here at Square Solutions. Basically, Square Solutions is a Viennese company, as probably most of you know. I had the opportunity to also join the Square journey to our new Munich branch. So from time to time, I'm also in Munich now, to basically, help the team there to kind of get into the same shape as we're in Vienna already. And I would like to start this talk with, a little bit of a story, which basically gives you a little bit more context on what I'm talking about and why I'm talking about this. And the thing is that in software engineering, as I said before, we have this age-old problem, right? Which is, I think, first phrased by the mythical Manmans and then since then rephrased and rephrased again. And it basically says the more people we put into projects, the slower we get, right? So the more and more people we put into projects, the slower we seem to get, the slower we basically deliver new features. And I guess that's not true for software alone. I think that's true for many organizational aspects, but it's obviously something which we didn't fully overcome yet, right? And I always realized this good friend of mine who also works in a startup, and who was one of the founding engineers there. And basically, he said the other day to me that, I had the feeling that we delivered more features when we were 4 people than we are now with 75. And I think that nails it down to the point that if you scale this further to 1,000, to 5,000, to 20,000 people, right, we obviously have this problem that we at some point in time have the feeling that we don't deliver anymore, that we are not able to deliver anymore at a certain scale. And in addition to not delivering, our systems, unfortunately, these days suddenly become more and more unstable, right? We have outages and all these things which we basically don't want to have. And this is where we usually end in the domain of complex systems, right? And we call this complex system because it sounds, of course, much smarter than saying, I work in a system where we didn't deliver any value for the last 3 months, or I work in a system which goes down every 24 hours, right? So usually we say we are working in complex systems, and that's fair. But as we've seen by both curves, it basically brings us away from what we usually want to achieve as software engineers. And I like here the quote from Dan North a lot, where he basically says, our job is to safely and sustainably reduce the lead time to thank you, right? That's what we want to do. So software engineering itself never has value on its own. It basically just brings value when we basically create some impact, when we reduce the lead time to thank you for our customers. And software always starts the same way, right? Somebody has a great idea. Somebody comes into the room and says, "Hey, I have this great idea. I want to do this," and he probably does it. Though there's nothing better than a great idea, right? And this idea is then implemented in a simple system. The idea seems to work. Maybe it even generates some money, and the system gets bigger and bigger. That we at some point in time end up in a complicated or maybe even complex system. I will talk about this a little bit later. And at some point in time, it obviously makes sense to think about, hey, what do we need to do now, right? We have more and more people in this team, so we need to modularize it. So we need to basically start to introduce abstractions, and we are the best ones, right? Our industry is the best ones in introducing abstractions. I think there's no other industry that built so much up on abstractions, right? If you think where we started with 0 and 1s, right? And if you take all these layers, basically, we are the godmother of abstractions. And abstractions make a lot of things very useful in our industry. And obviously, we need them when we get into complicated systems, that we abstract complexity away by introducing modules. And I think we all can agree that this is a very useful practice, right? Modularizing systems. I just had the feeling that over the last couple of years, we went somewhere into a wrong direction when it comes to this part, right? Because modularization is these days often equalized with distribution. So when we say, hey, we need to modularize our system, the first thing is we basically slice this stuff up into smaller systems by something like a service-based architecture. So modularization and distribution are obviously not the same things, and I think that's very important to express this, that we have on the one hand side modularization, which can be good or which can be bad, right? And on the other hand, we have the number of deployment units, which can be very monolithic or which can be very distributed, right? And unfortunately, in many cases, we are living in a bad modularized monolithical system, which we tend to call a big ball of mud. And I like here the phrase of Joseph Joda, which basically says that sadly architecture has been undervalued for so long that many engineers regard life as a big ball of mud as normal, which obviously should not be normal. But in many cases, we are in this situation where we have bad modularization in a monolithic deployment unit or more monolithic deployment units. And our answer, unfortunately, I think didn't really get the point, right? Because what we often then did is that we said, okay, let's distribute this stuff, right? Because distribution is modularization, which is obviously not true, which led into the fact that we have a bad modularized system with distributed deployment units, which we tend to call a distributed monolith. And a distributed monolith per se is, I think, a very bad term because it implies that the monolith is something bad. And the monolith is just a definition of how we deploy our stuff, right? So basically, we should probably call this a distributed big ball of mud or something else. But what we actually need to do when we just want to solve the problem of modularization, that we can still stay, for example, in a monolithic deployment and do something which we tend to call these days a well-structured monolith. And the point I want to make here, which I think is very important, so probably if you take one thing from this presentation, then it's this, that distribution and modularization are two different things, right? And we should not mix them up. And there are a multitude of good reasons to go for distributed systems, and the rest of the talk, we will talk about distributed systems. But modularization is not one of these, right? And I like the definition of Simon Brown here, who usually says, if you can't build a well-structured monolith, what makes you think microservices are the answer, right? So modularization is obviously not a factor for going for distribution. And I work with distributed systems, I would say, my whole career. So what is then obviously what makes distributed systems so valuable, and in which situations do we usually go for them? And there's a multitude of reasons, of course, to go for distributed systems. And I usually group them into two groups. They're the technical means, which we all know, right? For those who read some Newman books about microservices, they know the technical means for microservices or for distributed systems. To say, okay, we want to have individual scaling, right? We have 10x traffic on the one part of the system, but it should not affect the other part of the system. So we can independently scale up parts of our system. Of course, a reason to split up a monolithic deployment unit into multiple ones. Or we could say we want to be technology agnostic. We want to support technology segmentation by saying usually we build our microservices in Go or our services, and we build a new one, and this one needs to have machine learning attributes and stuff like this, and we have probably with Python a better ecosystem to do so. Or we want to co-locate things, right? We say, hey, we want to really bring things to the edge. We want to bring them as close as possible to the customers, and usually all our system runs in Germany, but some of the parts should basically run on the edge, so we deploy them directly at our clients in the United States. And these are usually the technical means which we see as foundation to go for distribution, where we see as reasons to basically split out our system into multiple deployment units and multiple runtimes in the end. But on the other hand, I think these are the reasons which usually don't move the needle, right? Usually we go for distributed systems, at least from our observation and from my observation, for a total different set of reasons. And these reasons are usually organizational ones. We go for distributed systems because we basically want to achieve autonomous teams, which basically can take ownership of their part of the system, of their part of the product. So this famous, you build it, you own it, or false, you build it, you run it, right? And you could now argue, but why, right? Why do we need distributed systems to achieve autonomy in the teams, to achieve that teams can basically take responsibility? And that's a very valid question, which I discuss very often these days. And the point is that you usually cannot expect from this team, which should own module C, taking ownership of this module C if it runs on the same deployment unit, then the module B from another team. Because if this team breaks up something, the chances are quite high that this will affect our whole system, right? So if I would be part of this team, I would say, yeah, I can build stuff in module C, but I will never take full end-to-end responsibility of this part, because in the end, everybody within the single deployment can lead to the fact that my part of the system is not working anymore. So we actually want to enable teams to work autonomously, right? And of course, if this is not a case for you as an organization, then probably a big value of distributed system goes vanish in the first place. So what I want to bring out to the point here is that distributed systems are usually a social technical thing, right? We don't introduce microservice for pure technical demands. We introduce them because we basically figured out when we want to scale organizations in terms of being able to deliver more value and to deliver it more efficiently, then we basically need autonomous teams. And basically we can achieve those autonomous teams only if we can give ownership to those teams, right? So we optimize for autonomy. And we hear autonomy all the time, right? In every meeting we hear things like, we need autonomous teams that can take ownership. You build it, you run it, all these things, right? But I often have the feeling that we are not really aware of the consequences of what we mean by autonomy, right? I'm not really sure if we just optimize for autonomy, not understanding what this basically means. And autonomy never comes on its own, right? Autonomy always comes as a consequence, and this consequence is responsibility. And if you fully optimize for autonomy, right, but don't give the teams responsibility, then you probably end up in the zone where the ops will hate you, right? They will just quit probably, and they will say, hey, the teams do whatever they want to do in whatever technology they want to do, however they want to do it. They build it on their own way, but we are responsible for running it for them, right? On the other hand, if you say, your teams should be full responsible, but cannot make their own decisions, are not independent, are not autonomous, then this is probably the zone where the devs will quit you, right? So we need to obviously be somewhere around this blue line, where we say basically we need to have a good trade-off between the responsibility we can give to the teams and the autonomy these teams need to take this responsibility, right? And of course, if you go for you build it, you run it, and you build it, you run it, even says it, right? You build it, right? You have your full autonomy to build the stuff however you want to build it, but you also run it, right? So you have the full responsibility. And usually we are not there in Central Europe, right? We have rare the cases where we really have you build it, you run it culture in organizations where teams can really make on-call rotations and things like this. So we're probably somewhere around here, and that's not a problem, right? It's fine if you say we have a you build it, you own it strategy, or you build it, you care it, whatever it is. But I think we need to first really need to make this decision. And this decision is not, okay, do we have autonomy or not, right? The decision is how much responsibility do those teams really want to take? And based on this, we can define how much autonomy we want to give them. So actually, we optimize for responsibility, right? That's what we are doing. And therefore, teams strive for autonomy, or teams need autonomy. And by doing so, as I said before, this is basically the hypothesis which our industry builds up for the last 10 to 15 years, right? That we say, if we build more autonomous teams, right, then those teams will end up in a way where they can independently work, and where we overcome this issue of scaling software by saying, hey, you as a team, you're on your own responsible, so you can basically make it work so that you deliver at scale, even if we scale organizations and introduce new teams all the time, right? And this is where we usually want to end then, right? So that we say we have an autonomous service-based system, which is well modularized and which is distributed to achieve the mean of autonomy. And the modularization is, of course, essential so that these teams then really can work autonomously, right? And as I said before, we often saw, this decomposition fallacy, where we had this big ball of mud and we wanted to go up there, right? So we wanted to go into autonomous service-based systems. And when we do this, we realize that this needs a lot of skills, right? This again needs this, this wholly three-folded understanding of the product, the organization, and the technology. And it also needs a lot of experience in how to basically decompose systems. And in many cases, if you do this, right, you probably will end up more like there, right? And if you end up more like there, this is usually, I would say, a huge problem, because we realized, or at least our understanding and our experience, is that it's very hard, when not even impossible, to get from there to there, right? So there's this hidden wall of, refactoring distributed monoliths into well-structured distributed systems is something which is, a challenge on its own. And in many cases, we probably will end up in, first going back into this direction. This is where you see then teams shifting microservices into monorepos again, right? Having monolithical deployments, basically restructuring stuff there, and hopefully at some point in time ending up in autonomous service-based systems again. So if you're currently in the stage of decomposing your badly modularized monolith, then start on the vertical first, right? Really go into a well-structured monolith first, usually, and start to decompose this then into autonomous service-based systems, right? So of course, not everything is black and white, and just as a general disclaimer, all on the slides is highly simplified, right? There's never, an answer which can be solved that easy as it is probably presented on the slides. It unfortunately always depends, but our experience showed that usually, if you want to go from a big ball of mud to a well-modularized distributed systems, then start with the modularization and not start with the distribution. And what's quite interesting is that the change in the cause of the failure which exists when we shift from monolithical deployments to more distributed systems, because traditionally we have the cause of failure is reliability, right? We expect from a system that if you say, hey, sum up 2 + 2 give us 4, right? That's what we basically optimize for. So we have tests, we have test bases, we do test-driven development. We invested a lot as an industry to overcome this problem of reliability. And of course, this problem of reliability still exists even if we go into distributed systems. But the interesting part is that a completely new problem comes up, so to say, which is availability, where we don't have, this well practices to basically overcome this problem. And I do a couple of workshops from time to time when it comes to distributed systems, and I always ask the same question to the people which are in this workshop. So I ask them, what is the difference between a method call within a single deployment unit? So we have module A, we have module B, they all resist in the same deployment unit, and we basically call create a user in module A, and this calls a function create a user in module B, right? And what's the difference between this and the method call across the network? So basically, same business requirement. We have service A and service B, and we basically go over the network to create a new user. And the answer is quite interesting, right? People then say, yeah, the one thing is maybe more complex than the other, right? We have the issue of network, we have resiliency issues, we have retries. And if you sum up all the reasons, basically everything is different, right? Beside the fact that we want to create a user, suddenly, if we go for distribution, everything becomes more complicated and becomes even more complex, right? Because if you think about this, there will always go something wrong, probably, why you cannot ensure that a user can be created. And the reason for doing that, for this going wrong, is a multitude of reasons, right? We have a misconfigured service, we have a outage of a service, we have a misconfigured VPC, we have a misconfigured network, whatever it is. And people actually summarize this quite early with the fallacies of distributed computing, which basically say as soon as we start to go over the network, as soon as we go for distribution, obviously, things get inherently more complex because the network is obviously not reliable, the latency is not zero, the bandwidth is not infinite, the network is not secure, and the topology does, of course, change and many other things, right? So as soon as we go into the area of distributed systems, and by doing so, we basically had the goal that teams can start to work autonomously. We suddenly often realize that we have, a huge spike when it comes to the issues, when it comes to the downtimes in our system. And this is exactly where we need to hit in as architects, right? Where we basically need to optimize our system to basically make this autonomy really work, and to basically also optimize for the availability which we inherently need when we go into distribution. And I often have the experience, or I often make the observation that we don't fully get this yet, right? We often start to treat distributed systems the same way as we would treat monolithic systems. So we don't really tackle this effect of availability. We basically treat especially the effect of reliability. And you see this quite well if you go into an organization. Let's say we have here the banking domain. So there's a loan team, which is, shouting around, which is pissed off because obviously the system is not properly working. People who should get a loan don't get a loan, and people who should not get a loan get a loan. So basically, they say, hey, something is not working, and we figured out what it is. Some of our downstream system doesn't react correctly. Some of our downstream system obviously sends back wrong responses or doesn't send responses at all, right? And what they then do is they run for a couple of days or even weeks through the whole organization to figure out what is basically the root cause. What made, this system unavailable? What made the system go down? And they probably will figure it out, right? They say, hey, the account team, okay, they have a misconfigured service, right? It returns 500s all the time. And basically, this makes our loan logic not work anymore, right? And also, this is maybe possible, right? Depends really on the scale of the organization. At some point in time, we're in such complex systems that, figuring out the cause of an effect is really hard. But in some situations, it probably works out. But the thing is, it's highly inefficient, right? Because if they now go to the account team and tell them, hey, please fix your stuff, well, then probably they put it on a backlog and they will do it at some point in time. But as soon as they fix that stuff, probably there's, another misconfigured service. There's a database which goes on. There's a network which is, not reliable. And, things will break all the time, right? And what we're striving for is obviously a reliable system, a reliable ecosystem, or a stable environment, which is actually not existent as soon as we go for distribution, right? There is no stable environment. And the sooner we realize this, the better we are off. So we therefore need to strive for resilience, obviously. And what I mean by this is that, for example, if we have another domain where the payment service, right, where the payment team who is taking care of payments, let's say in an e-commerce domain, basically needs to execute payments and is again shouting around, right? They are not happy because they cannot execute payments right now, and they come to you maybe and say, hey, we cannot execute payments, it's a disaster, because the account service messed up something in their service, and basically therefore we cannot fetch new users, or we cannot fetch users at all, and that's the reason why we cannot execute payments. This is the reason why we return 500s, right? So the first question should actually be, is it really the accounts team's fault if you cannot execute payments, right? Because you as a team are responsible, obviously, for the subdomain of payments. You are responsible that this organization, whichever organization this is, can execute payments. So you probably need to figure out a better way than returning 500s if the accounts team does not can return you the current users, right? And of course, the first thing would be to make it more resilient, to say, okay, we don't return 500s, we just return a message and say, hey, sorry, we cannot execute payments right now. We're really sad about this, but maybe come back a little bit later, right? But probably that's not fulfilling, right? If you think about an e-commerce domain where payment is basically everything, because in the end, you can buy a product or you cannot buy a product, depends highly if you can pay for it or cannot pay for it. And probably, the competitor is just one click away on Google. So you basically need to ensure the availability of payments being very high. So probably you need to come up with better architectural concepts, where we then often go for the idea of just introducing a cache, so that we basically can at least do payments for users which we're already aware of, right? Or going more into this idea of event-driven and reactive systems, where we say we publish basically events whenever a user is changed, and everybody can build up its own read model, its own projection, hydrated based on the user changed events which somebody else produces. Okay? Of course, this introduces a lot of complexity again when we think about eventual consistency and when we think about, additional data storage and things like this. But if we really want to optimize for availability and for, giving the team the responsibility that they are fully responsible that payment is up and running, then that's probably architectural decisions which make a lot of sense, because suddenly, even if the all account service goes down, we can still execute payments, right? But also in the other direction, we need to do this. If we know, hey, there's another team which is calling us, right? And then the chances are high that this team at some point in time will have maybe a misconfiguration somewhere and the DDoS our system. So we need to basically ensure that we have proper load balancers, circuit breakers, or maybe even caching again in place, so that we basically know, okay, this can happen, right? This is out of our control zone. We really need to be aware of this. We need to build our system resilient when it comes to the outside world, outside of our team scope. So the first, probably most important thing is to architect for coding environments, right? To really understand, hey, our environments at some point in time will be coding, yeah? There is no guarantee, or there is basically no possibility that in distributed systems we will have stable environments all the time. And I really mean this by saying that we basically really start, or need to start, to dance with the beast and embrace chaos. And one way, of course, where I said before that we don't have good metrics or practices yet for availability, is of course chaos engineering and introducing, for example, game days, where we say, basically, if we want to optimize for availability, right, the same way as we optimize for reliability by improving our test base, we can basically just optimize for availability by doing some chaos from time to time, by saying, hey, what would probably happen if we play this funny chaos monkey, or this clown who basically turns out the database? How will this affect our system? And you would probably ask yourself, no, but why do I want to do this, right? Why do I want to trigger this pain, right? And of course, the thing is, this pain will at some point in time happen. The question is just when, right? And the question is, are you planning for tackling this pain then? Or is it somewhere at 2 o'clock in the morning when one crookie developer is on call rotation, who basically needs to figure out, hey, how do I deal with a broken database then, right? So I usually like to have my production environment coding from time to time. On a Wednesday at 2 o'clock, when everybody's aware, hey, we will shut on the database now. Let's go through our procedures and figure out how our system will probably react when this database suddenly goes down. What do we do? And we can, of course, introduce chaos in many different parts of the system. But the thing is, a service that can run in a stable environment can run everywhere, right? But a service that can run in a chaotic environment can run everywhere. Sorry, I just messed it up. A service that can run in a stable environment can, of course, only run there, and the service that can run in a chaotic environment can run everywhere. And as soon as you understand this, you probably don't have any other option than to go for resilient systems, to basically go for systems that can also deal with chaotic environments, right? And of course, it's always a question of a trade-off, right? How big is your system? How big is your organization? The bigger the organizations, the chaotic, more chaotic will your environments get, the more you need to invest in, building services that can also survive in chaotic environments. So architecting for chaotic environments is always something which should be a very important part when we think about scaling architectures, when we think about scaling organizations. But there's another one, right? Let's assume again this example where the payment team is again, shouting around and saying, hey, we cannot execute payments because the payment gateway team messed up something, right? They have an issue there and therefore we are blocked and we cannot do payments, right? And there's, of course, a hidden elephant here on the slide, and you would probably ask yourself if you come into the station and say, "Hey, if executing a payment is such an important customer journey, right? Why do we distribute it about across two teams? Why don't we say, hey, you as a payment team, you're responsible for payment end to end, right? The user click on the payment button until it lands over the payment gateway at one of the payment service providers. So why don't we go for end-to-end verticalization? Why don't we go for a team structure and say, hey, you as a payment team, you take responsibility for this? And of course, I know the answer. The answer is unfortunately always cognitive load, right? To say, hey, payment itself is so complicated, maybe even complex. We cannot deal this as a single team. It's impossible, right? This team will be out of cognitive memory all the time, and they will not be able to handle this problem. So you still think, okay, but how do we reduce the cognitive load, right? It's maybe a possibility to slice the vertical thinner, to say, okay, we split up this payment team now into two teams, and one is end-to-end responsible for credit cards, and another one is end-to-end responsible for SEPA payment. And by achieving this end-to-end responsibility, you of course achieve the thing which we mentioned earlier, that we basically want to achieve team autonomy and teams taking ownership. And you usually only get into this direction if teams really start to have end-to-end responsibility. And this sounds now very romantic, I know this, right? And of course, we will have dependencies between those teams. It's impossible to slice organizations in end-to-end, fully autonomous, independent, end-to-end verticals, right? That's not given because otherwise we would probably not benefit from each other if everybody, lives in its own silo without any interaction to the outside world. So of course there will be dependencies, and especially if we slice our systems based on end-to-end responsibilities, we will see this dependency mainly across data. So we'll basically come into the fact that, if you do credit payments and you do SEPA payments, then you probably share accounts, right? Because probably an account can do a credit payment and a SEPA payment. And that's quite interesting. And that's what I usually tend to call the customer journey entity data mismatch problem, which I think is quite interesting these days because we made a switch. And I think we made a very important switch that initially when we build distributed systems like microservices, we often structure them around entity data, right? So we had this entity service anti-pattern, how we phrase it these days. We had a user service, we had account service, we had a transaction service. And whenever we wanted to basically do a payment, we needed to go through all those four services or three services. And the problem was, of course, that these systems are highly irresilient, right? Because in the end, for each value customer interaction, we had, this distributed monolith again, where basically said none of these services on its own can bring value. It always has a dependency on other services along this customer journey, which ultimately brings value. And this is basically why we end up also in the situation that our systems don't really have the needed effects which we expected. So we started to slice them around customer journeys, right? Usually organizations start to do this or are already doing this and say, we have a team responsible not for user, but responsible for payment execution. We have a team responsible for user onboarding, and we have a team which is responsible for fraud detection. So real value bringing end-to-end journeys, use cases. But the thing is, of course, that we have an overlap here, right? Payment execution probably needs a user and probably needs accounts, and even maybe transactions. And user onboarding needs probably users and accounts, and fraud detection probably needs accounts and transactions. So you see an overlap there, right? All of these customer journeys obviously need accounts. So we will have the dependency on data usually when we slice vertically. And what we need to do, first of all, is we need to figure out who is responsible for this data, who is the real owner of this data. And once we make this decision, we again have the same situation. We can, of course, ask, with a REST call, hey, give me the current account, right? Or we will end up in the situation that if this service is not available, we probably don't have the account. So we, again, probably want to go for something like reactive or event-driven systems, where we basically, invert from a pull-based to a push-based system. And I think it's one of the most important things that we really architect for this end-to-end responsibility, yeah. As I usually say, and I also teach at university from time to time, and I teach software architecture there, and I always say software architecture was very easy a decade ago, right? Because it was mainly technically driven. You said, okay, you put your persistence part there, you put your business part there, and you put your front-end part there, right? But these days as an architect, you unfortunately need, unfortunately, yeah, we could argue about this, but you fortunately need to understand the business, you need to understand the product, right? You need to understand how is our product actually composed, what are the value-bringing streams. You need to understand the organization, and you, of course, also need to understand the technical means. And if you bring all these three things together, you bring a lot of value, obviously, and you can basically architect for these end-to-end responsibilities, which is again a precondition that we really can end up with these autonomous teams. And of course, as I said before, live organizations are not silos and should not be silos, right? So we usually trade this end-to-end responsibility, or we trade dependencies on this end-to-end responsibility for decreasing cognitive load, right? There's always this trade-off be saying, hey, I want to be fully on my own, right? But then I need to do everything on my own, which gets inherently complex, right? And which I probably will not achieve, and I don't want to rebuild the wheel again and again. So obviously, I will need to take some advice from the outside, right? So I will have some dependencies, and the idea of these dependencies is always to decrease cognitive load, right? And in this example from before, and I used the pattern language now, which was introduced by team topologies, so stream-aligned teams, right? These are teams basically which have one goal, to bring customer value to our customers. And I like this book, first of all, because it introduced, I think, this very simple pattern language of those 4 teams. And I will go through 3 of them. And basically, when we say we have these stream-aligned teams, then we will often end up in the situation that, as I said before, we want to optimize it for end-to-end responsibility. And we need to then squeeze out cognitive load from this end-to-end responsibility, because others, on the other hand, we will not achieve to have a very long vertical, right? Because we will have very short verticals if we cannot kind of guarantee that we put load out of the stream-aligned teams. And this is usually where we introduce in complicated subsystems. Again, for example, in our case of SEPA payment, fraud check is something that is so complex that it cannot live just, as part of a team. So we say, hey, you take care of fraud checks, right? And basically, there's not so much difference between a stream-aligned team and a complicated subsystem team, because, as I said before, for a stream-aligned team, the reason for existence is to bring customer value, in that sense. And a complicated system also has a reason for existence, and again, it's bringing customer value. But for a complicated subsystem, the customer are basically the stream-aligned teams, right? So their responsibility is essentially and only to basically reduce the complexity within stream-aligned teams, in our case, the SEPA payment team. So if they're not good in doing that, there's no reason for existence, right? If the SEPA payment team says, hey, they make our life even harder, right? If we would just kind of, take the service, taking our responsibility, life would be easier, then there's no reason for existence for complicated subsystems. So they always should optimize to make the life of the stream-aligned teams easier. And if we now have this dependency on complicated subsystems, we always again could run up in the situation that we need to understand what is this dependency, right? What's the mean time between failure? What's the availability of the system? To architect around it. And usually there comes up this famous nines, right? So we really need to understand what are the nines of this dependency. So do we have a 3-9 dependency, which basically leads to the fact that we have a downtime of 9 hours a year, or do we have something else? And again, in my workshops, I usually then ask the people, is it actually possible that our streamlined team here can still have a 4-9 availability if our complex subsystem dependency has a 3-9 availability? So is it basically possible that we achieve here 4-9 availability while we have here a 3-9 availability? And usually the answer is somewhere around 50-50. And of course, it's possible. I mean, it depends a little bit how you see availability, but that's actually our goal as architects, right? To exactly achieve those things. When we understand this system has a 3-9 availability, right? Then we can, of course, optimize this system that we have a 4-9 availability there by saying, you know what? When we expect the system to be down 9 hours a year, that's too much because we basically just want to be down 5 minutes a year. Then we introduce a rest scheduler, right? So we basically don't say, you know, your payment is not working, but we say your payment will work, right? And we guarantee this for you. So we increase, of course, the availability. And introducing the complexity of a rest scheduler makes probably sense if your complicated subsystem has a 3-9 availability, but if it has a 5-9 availability, then you probably need to know this because you know then what's the point of building a rest scheduler if your system is down 5 minutes a year and you probably just say, okay, 5 minutes is enough, is fine enough, right? So we basically just send the error back to the user and say, hey, sorry, your payment didn't work for whatever reason. Can you just quickly retry? And chances are quite high that it will then work again. Right? So what I'm saying is that we always need to understand the non-functional requirements which those dependencies give us, right? And especially in the context of team topologies, we need to understand what do teams that should reduce the cognitive load on our streamlined teams, like complicated subsystems, also platform teams basically give us what is the developer experience, what a service level objectives or agreements which we can expect, right? And I don't say that you need to have the nines for each of your dependency within the organization, right? I mean, you can basically achieve these things quite easy if you have proper monitoring and tracing in place, but you need to have an understanding what is basically this dependency? How do I need to deal with this? And I often have the feeling that we treat dependencies as something exclusively negative, right? So a dependency is always bad. But the thing is, a dependency is not equally bad. You can have dependencies that are a little bit less bad than other ones, right? And in the end, as I said before, dependencies give you the trade-off that you can depend on something, right? It even lives in the term. And I like the definition from Verfladik because I think it basically gives us a good option to better discuss about dependencies and to discuss about the pain of dependencies. Because it says basically dependencies kind of come out of three things. The strength of a dependency, how strongly are you coupled on something, right? The distance, how far is the dependency away? So basically, you have a dependency within the class, right? From a method to another method, the distance is very short, right? But you have a dependency to another service, right? Living on the other side of the world, operated by a completely other team. The distance, what is this dependency, is obviously very, very high. And last but not least, the volatility. How often does this dependency change, right? And the interesting thing about his hypothesis is here that the pain of dependencies is basically a multiplication of all the three factors. And those who are good in mathematics probably know that if you do multiplications, you basically just need to optimize one thing to zero, and this will lead to a result of zero. And I think that's very valuable if you think about this, right? Because if you say, hey, we have no volatility in change, right? Because this system will never change, right? It's basically maybe just a JSON file put in a S3 bucket, which we depend on. Then, of course, neither the strength nor the distance of the dependence is such a huge problem, right? So we really need to think a little bit more differentiated about our dependencies, and we really need to architect for low dependency pain. Therefore, we need to understand our dependencies. And last but not least, when we architect for scale, I think it's very natural that we unfortunately not start from the green field, right? I always say it's easy to start from a green field. Everybody can do this. I want to start from a brown field. And in many situations, we have, for example, a legacy system. And let's assume again this case where we have fraud checks in this legacy system. And we now restructured maybe our organization and we said, hey, we want to have teams that can take more responsibility and more ownership. So we basically say, hey, you are the SEPA payment team, and you basically also need to involve in the fraud check because you should have end-to-end responsibility of SEPA payments. And the best way to do this, but that's a talk on its own, is obviously, in my opinion, the inverse convoy maneuver. To not, first of all, kind of restructure how our system should look like, but first of all, restructure how our organization should look like. And based on this, the organization will drive the architecture, or in Conway's law terms, the architecture will follow the organization. So if we have this big legacy system, then we should first of all think, hey, which teams do we want to have? Which responsibility should they take? So we say, okay, we want to have a payment team, a SEPA payment team. And this SEPA payment team should be responsible that we can always execute SEPA payments, right? And then they naturally, if we give them this task, will start to carve out things of the monolith or of the legacy system. They will start to carve out things which are useful for them to achieve this goal, right? They probably will not carve out the whole monolith and will not say, hey, we do this and that service and this and that service. They will probably just take the things out which really help them to achieve the goal that SEPA payments can be executed, right? And we can do this then for multiple teams, of course, and this basically helps us in decomposing the monolith where it's useful, right? Because I think we should also stop with the illusion that it makes sense to 100% decompose monoliths, which have been there for decades, right? But let's assume we do this. Let's assume we have now this team which takes parts of these monoliths out of this legacy system. So basically, they take the fraud check, which is the light gray box out here, and build up a beautiful API around this and say, hey, nice, we have this new fraud system now, which is carved out of the monolith. And we all know that monolithic composition is hard because what's really hard is decomposing out the data, right? And let's assume we do this, right? Let's assume, okay, we say, okay, we decompose the data. So at some point in time, we will switch over the readers and writers from left to right. And then we basically need to have decomposed the logic already. And then we basically need to just shift over the user fraud data from right to left. And this, of course, introduces downtime because we, of course, need to shut down both systems, need to say, okay, we need to shut it down because nobody should create new user fraud data when we transfer this data from right to left. And basically, at some point in time, we obviously, hopefully, have shifted over the data from right to left. And this is usually happening on a Friday night, right? When everybody actually wants to go home. And once the downtime is over, we will figure out, hey, this reader is not working on this new API. This API throws errors for this reader. So this reader cannot read data now. And then people say, okay, then let's go back, switch the reader back. Of course, we cannot do this, right? Because then we will run in a fully inconsistent state. And then, we probably need to turn this around again, right? Need to revert our data migration. We'll have downtime again. It's probably already Saturday morning. We will probably fix the API at some point in time, and we will do it again, right? Go into downtime, migrate the data over, shift all our readers and writers at the same point in time. And these are really the situations that personally give me a heart attack, right? These are the situations where I don't want to be involved anymore, to be honest, because these are the situations that make everybody feel bad and that usually often feel to failure, right? These big bang migrations, which always end up being a big bang, and this big bang, is usually very painful. So what I would like to do is that I say, we build up this new service, makes full sense, right? And we basically start with the data first. So we start to replicate the user fraud data by each user fraud event, which basically updates this data. So we can, for example, go with methods like CTC or many others and build up here a read projector read model. And by doing so, we can basically already shift over the readers. We can tell the readers, hey, go to this new API, it's beautiful. You can read their user fraud data from there, right? And the thing is that we who decompose this part of the system usually say, hey, switch over to this API because this API is much more beautiful than the old one and better and faster and everything. And it's RESTful, right? And we have GraphQL in place. But usually, the dependence on these legacy systems, they don't care, right? To be very honest. And the problem is, if we do this, we have obviously a reader-first migration. So we need to migrate all the readers first until we can migrate writers, because writers still need to write on the right-hand side, because as soon as we still have readers on the right-hand side, we need to have the source of truth on the right-hand side. So we need to migrate first of all the readers, and at some point in time, we can probably then also migrate the writers. And the thing is that this is usually a very big organizational challenge, only migrating readers, because readers and writers are usually in the same teams. We have basically teams which we tell, hey, migrate to the new system. If we tell them now, hey, but first migrate the readers, and a year later migrate the writers, they will probably, put it on the priority very low in the backup. So what we usually want to have is we want to have this in both directions. So we want to say, okay, and if we, update user fraud data on the left-hand side, we again produce events which are landing then on the right-hand side. So we can simultaneously shift over readers and writers. We can simultaneously shift over whole teams from the left-hand side to the right-hand side. And we can do this and do this and do this until we probably figure out, okay, there's again a writer with a failure, right? So something is not working on this writer. And the nice thing is that we can basically just shift it back, can go on weekend, right? And can start to fix it on Monday with a fresh head and basically shift it back again, right? And this is how I want to have my migrations done, right? So that I can step by step migrate systems and services over, with low NCNT of change, because people will probably know, okay, if something goes wrong, we have the safety net to basically go back without, big downtimes, big migrations, big Friday and Saturday evening sessions. And at some point in time, we can obviously shut down the old system. And this is just one example, zero downtime migration, but we have a lot of other techniques these days when it comes to architecture, where we can ensure this part of, building systems that actually enable us for change without being afraid of change, right? So we have canary releases, we have dark launching, we have the scientist pattern. So basically came a lot of patterns up over the last couple of years to basically support us in doing that. So architect against change anxiety, which I think is very important and very a very interesting part when it comes to architecting for scale. So we are nearly at the end of the time, so let's quickly sum up. So for those who are not so deep into distributed systems yet, probably the most important takeaway from this talk is that modernization is no good reason to go for distributed systems. Usually autonomy is, right? And if we then go for distribution, we usually shift from monolithic deployment units to distributed deployment units, of course. And the problem that basically we get then as an additional one is the problem of availability. And to solve this problem of availability, we basically need to architect for coding environments, right? We need to understand that things will go wrong, right? The definition of distributed systems, everything that can go wrong will go wrong, right? We need to architect for end-to-end responsibilities that these teams can really take ownership. And last but not least, we basically need to architect for low dependency pain. So we really need to understand, hey, what are our dependencies, right? How painful are they? And how do I need to isolate myself or not isolate myself from them? And last but not least, within the teams, I think we really need to introduce good practices to architect against this change in NCNT, so that teams are really eager to make changes. They're really, kind of also happy to tackle the hot irons, which are usually painful if we don't invest in practices and tools like this. And by doing so, by just following these four simple patterns or these four simple advices, and there are of course a lot more. And as I said before, things are much more complex in reality than I probably showed them on those slides. But if you follow those four, I'm quite eager that you will probably keep the flow of value high and the number of outages low, and basically keep the lead time to thank you low even at scale. Thanks a lot. I hope this was useful, and I'm happy to answer some questions now. Are there some questions? Let me quickly check this on my side. So somebody said, when trying to slice services alongside customer journeys, how to integrate external entity services which often manage certain user data entity service. Most of other journey services depend on? Yeah, that's a very interesting question because it comes down to the thing which we always need to deal as a software architects, which is basically deciding on verticals versus horizontals, right? And I probably could have made the opinion here now that I'm always striving for verticalization, right? But in the end, there's a price for doing so, right? So there can be reasons where we say, these classical horizontal layers can be useful, right? So we can basically always need to figure out what has the chance to change more often. Is the chance to change more often within a vertical where we need to then touch the end-to-end vertical, so it makes no sense to basically separate it across horizontals because then we have again this ripple effect and we need to touch many horizontals the same way. But on the other hand, authentication or authorization and many other cross-cutting concerns are usually good ways to basically say, okay, we maybe want to have horizontals, right? I mean, in this specific example, we could probably also go for micro gateways, where we say we basically deploy to each service its own gateway, which is still configured centrally by a control plane, right? Or we could say we basically just provide libraries which those teams can integrate into their services, right? Or we say we make a very, very thin layer of a gateway which basically handles authentication authorization, right? So again, it depends, unfortunately. There is no silver bullet answer to this. But I think this question is very good because it nails it down to the point, right? It's in the end about verticals and horizontals. And there is obviously a trade-off in both directions. Okay, any further questions? Now, David describes my daily hell of debugging and hunting down bugs in very complex service systems that are not within my service. Yeah, I try to really give you the story with this class, right, where people then are running down the whole organization. And I think this will scale to a certain amount of teams and people, but on the long run, it's basically not working, right? On the long run, it's unfortunately not effective. And on the long run, we really need to figure out what is the resilience we need and how can we decouple them from systems which are obviously very often breaking. So yeah, that's I think a good takeaway then. And I don't say, hey, build completely isolated systems, right? Build complete resilience, invest all your time in making your system or your part of the system super resilient. It's obviously a trade-off, right? It's elusive to say that if everything burns down, I can still deliver value as a team. Maybe you can, right? But then it's a huge investment and you really need to be aware that this investment then makes sense. Cool. So it's very hot in here, I need to say. So I hope you liked it. You can find the slides online as usual on our website. And you also probably, it makes sense to join this page from time to time or to look at this page from time to time. So we will have another Brainfood talk, I think in December, by my colleague Jose, who probably talks about something cloud native, as far as I know, Jose. I think it's not decided yet what he will share his experience on, but it's probably something about the context of Kubernetes or cloud native infrastructures. And probably if you join this page here, you find everything which we do from time to time in terms of community events, including these Brainfood talks, but also other things like meetups and stuff like that. So I hope you enjoyed it. I hope I was a good companion for your lunch. And yeah, see you soon.